Okay, so in this video I'd like to go over the element contributions to KFF, the structural stiffness matrix. Okay, so when you're looping through all the elements in a structural model, now you have some loop like this, like 4e in the range of the number of elements, right? Then for each element you want to figure out its contribution to KFF and then assemble it into KFF using that element's lookup vector. Okay, so what I'm going to go through is just kind of the process of forming the basic stiffness and then the local stiffness and then the global stiffness, and then we use lookup vectors to assemble global stiffness into KFF. Okay, so for each element in your model you know how to form the basic stiffness matrix. So if the element's just kind of oriented like this, the basic degrees of freedom are 1, 2, and 3. And it has, properties E, A, and I, and it has some element length L, right? And we can form the 3x3 basic stiffness EA over L 0, 0, 0, 4EI over L, 2EI over L, 0, 2, and 4, right? So you can make that 3x3, within your loop, okay? Then we want to transform that into the local degrees of freedom, all right? So this is basic degrees of freedom, and then the local degrees of freedom for an element looks something like this, all right? So this is, again, end I and end J, okay? Local corresponds to the longitudinal and transverse directions or axes for the elements. So 1, 2, and 3 are down there. 4, 5, and 6 are at NJ. Okay. So there's a matrix in one of the other lectures, I forget which one, but it's called ABL. All right, and this is a 3x6 transformation matrix which takes displacements and forces between the local and basic systems. Okay, so the basic stiffness matrix is 3x3. Okay, and then the local stiffness matrix is going to be 6x6. All right, and we can do that with the matrix triple product. Here, let me get rid of some of these stray marks. There's too much electricity in my hands or something, but at any rate, we can get the local stiffness matrix KL from the triple product of ABL transpose KB. Oops, sorry. This should be ABL on the right. Okay, and what that'll do is take the basic stiffness, which is in here, the kernel, right? It'll take that, and then you multiply on the left and the right by ABL transpose and ABL, respectively, and it'll transform these this 3x3 basic stiffness into a 6x6 local stiffness. All right, and I don't want to write out all the local stiffness. You can see it in your lecture notes. All right, but it's it has the rigid body modes. Like, this is EA over L, 0, 0, negative EA over L, 0, 0, and then the second column is 0, 12 EI over L cubed, I think it turns out to be, and then 6 EI over L squared, and then 0, and then dot. All right. It's a 6x6 matrix. But the point is, this triple product, this operation here, explodes this 3x3 matrix into this 6x6. Okay? And this ABL matrix, it depends only on the element length. All right? It's something like -1, 0, 0, 1, 0, 0. So that's -1. 0, -1 over L, 1, 0, 1 over L, 0, 0, -1 over L, 0, 0, 1 over L, 1. something like that. But it's in the notes, all right? But it only depends on L, all right? So it's easy to form, okay? All right, so we can get the local stiffness, all right? But in order to assemble it into the stiffness matrix into the structural stiffness matrix, KFF, we need to resolve that local stiffness into global directions, okay? Which coincide with the global directions X, Y, Z. All right, so 1, 2, 3, 4, 5, and 6. Okay. All right, so to that end, we form K. There's going to be another triple product, ALG transpose times K local, which is, right here, which we just computed, times ALG. Okay. So we're just exploding out, or basically not exploding out, but basically just rotating the local degrees of freedom into the global directions. All right, and this ALG matrix is really easy. Right? It's just based on the direction cosines for the element. It's like cosine, sine, negative sine, cosine 1, cosine, sine, negative sine, cosine 1. All right, and everything else is zeros. It's a little block diagonal matrix there. Okay, so that's that, right? And once we get the stiffness into the global degrees of freedom, we just assemble K, what we had up here, into KFF using the lookup vector for this element, which you get from the global equation numbers. Okay. All right. So hopefully that gives some idea of kind of the assembly process or the contribution of each element to the structural stiffness and how each element's basic stiffness is transformed out to global, and then you use the lookup vector. Okay. Thank you.